This is Foundations of Math and Pre-Calculus 10, Chapter 4.3. This time we're going to be looking at rational exponents. So, radicals can be expressed as powers. Sometimes rational exponents are easier to work with, and other times radicals are easier. It is best to get used to both methods. So, let's try to notice the pattern here. We have x to the power of 5 times x to the power of 5. This is x to the 5 plus 5, and that's equal to x to the power of 10. X to the 4 times x to the 4 is x to the 4 plus 4, and we have x to the power of 8. X to the power of 3 times x to the power of 3 is x to the 3 plus 3, and that's x to the power of 6. X to the power of 2 plus 2, hopefully you see the pattern by now. This is 4. X to the power of 1 plus 1, x to the power of 2. So if we have the square root of x times the square root of x, this is x. And this means we have x to the power of something times x to the power of something equals x to the power of something plus something. And remember, this box must be equal. Okay, so we need the same quantity in there and there. So the box equals 1/2. So half plus a half is x to the power of 1. So this must be x to the power of half times x to the power of half. Let's look at cube root. The cube root of x times the cube root of x times the cube root of x equals x. So the cube root of x must equal x to the power of what? That must mean we have a third plus a third plus a third equals 1. So equals 1/3. And take a guess at what the fourth root of x equals. I know we haven't done those yet, but this is x to the power of 1/4. Now, all exponent laws work for rational exponents. This is good because we don't have to learn any new rules. However, you need to recall adding and subtracting fractions. And also, you must reduce rational exponents before evaluating. Okay, so here we have x to the 3/4 plus 1/3, and we need to have a common denominator before we can add the fractions. And the common denominator here is 12. So we need to multiply this by 3/3, and we get 9/12. This one we have to multiply by 4/4, so we have 4/12. So we have x to the power of 13/12. Okay, and that's as simple as it gets. There's no simplifying after that. Sometimes it's necessary to change the base before using the exponent laws. Remember, we require the same base. Okay? And 9 is not a similar base because this doesn't work well. So we have to go all the way down to 3. So 27 is 3 cubed and 3/2. And 9 is 3 squared. And that's 2/5. Now, the easiest thing to do here is probably just to do the power of the power law and then do the division afterwards. So this is 3 to the power of 9/2. We multiply, and this is 3 to the power of 4/5. We need a common denominator before we subtract. This is 3 to 9/2 minus 4/5. And the common denominator is 10, so this needs to be multiplied by 5 over 5. So this is 45 over 10. And this needs to be multiplied by 2 over 2, so we have 8 over 10. And this is 3 to the power of 37 over 10. If it says evaluate, then you would have to actually plug that into your calculator. If not, if it says to simplify, you can just leave it like that. Okay, again, 4 is not the common base here, so we have to go all the way down to 2. So this is 2 squared, 3 over 4, and this is 2 cubed, 5 over 3. And again, we want to multiply using the power of a power law. So this is 2 to the power of 6 over 4, and this is 2 to the power of 5. We'll do one more simplification here. We want to reduce the fraction. This is 2 to the 3 over 2, and 2 to the 5. This is 2 to the 3 halves, minus 5, and the common denominator is 2. So 2 to the 3 over 2, and we multiply this by 2 over 2, we get minus 10 over 2, and this is 2 to the power of negative 7 over 2. Okay, here's a tricky one. And the problem that most people make is they forget to reduce this. And if we do negative 8 to the power of 2, we get 64. And to the power of 1/6, and this is equal to 2. But this is wrong. Okay, you need to reduce the fraction. Minus 8 to the 1/3. This is the cube root of negative 8. And that's equal to negative 2. And that's the correct answer. Now, we can do this on the calculator. Now, notice that I put brackets around the negative 8. We do bracket negative 8 raised to the power of 1 divided by 3. And we get negative 2. Okay, fortunately for us, the calculator also knows how to do raised to the power of 2 divided by 6. So it knows to reduce that fraction before evaluating, and we get negative 2. Let's run the Casio. Okay, bracket negative 8 raised to the power of 2 divided by 6, and we get negative 2. Okay, so just be aware of this and reduce your fractions first. Okay, there's 2 special bases, 2 and a half. 2 represents a doubling problem, and a half represents a half-life problem. And because these problems work on multiple of time units, it will have a slightly different form. So, what is the percentage of carbon-14 compared to a living sample of fossil that is 8,000 years old? And we use the formula. P equals 100% times 1/2 raised to the power of n divided by 5,730. So, just to clear up your understanding, the 5,730 is the number of years it takes to have the number of carbon-14 isotopes, i.e. the half-life. And what we do is we just plug it in. So P equals 100 1/2 raised to the power of 8,000 divided by 5,730, and that's approximately, let's clear this, 100 times 1 divided by 2 raised to the power of 8,000 divided by 5,730, and we get approximately 38%. And again, if you have a Casio, 100 times 1 divided by 2 raised to the power of 8,000 divided by 5730, and we get 38%. And again, the harder problem is to ask how old is the fossil if there is 20% of carbon-14 isotopes. Okay, so we have to guess and test. 100. And we already have 38%. And remember, this is a decay problem, so the bigger the number we put in, the smaller the value we'll get here. So we'll do 10,000 years divided by 5730, and we get approximately 30%. So that's not long enough, so we need to jump the time bigger. Try 15,000 divided by 5730, and we get approximately 16%. That's too low a number, so it means we went too big here. So let's try another number. We'll say 13,000. And we get 21%, and that's close enough. So about 13,000 years. Now again, you're not required to use logarithms, but if you want to try, this is how you do it. 20% equals 100% times 1/2 raised to the power of n divided by 5730. We want to isolate the power, so we divide both sides by 100. We get 20 over 100 equals 1/2 raised to the power of n divided by 5730. The exponent needs to come out front when we're doing the log, so we have log. 20 over 100 reduces to 1 over 5. N divided by 5730 times log 1/2. Okay, we'll divide both sides by log 1/2. But I'm going to move this over to this side first. N divided by 5730 equals log 1 over 5 divided by log 1/2. Okay, on this side we have divide by 5730, so we need to multiply both sides by 5730. N equals 5730 log 1/5 divided by log 1/2. Punch this in on a calculator. Looks like this, 5730 log, we don't need to put times. Calculator knows that it's supposed to be times. 1 divided by 5 and divided by log 1 divided by 2. And we get 13,305. Okay, that's a very accurate answer without doing any guessing and testing. And just to show you on the Casio, 5730 log 1 divided by 5 divided by log 1 divided by 2. And again, we get the same value, 13,305 years, roughly. And that completes this lesson.